In the last video, we talked about Gauss elimination method following with the back substitution method to solve system of linear equations with the help of matrices. The idea is first eliminate the coefficients from the coefficient matrix, or in fact augmented matrix, make them zero from the equations coming later on with the help of equations which is coming earlier. And once we get a triangular form of equations, so the first equation has, let us suppose, m variables, the second equation has m minus 1 variables, the coefficients are m minus 1, non-zero coefficients are at least or at most m minus 1, um, and then at most m minus 2 non-zero coefficients, and so on. And in the last we are getting only one variable with a non-zero coefficient. So while going for the back substitution, we first solve for the last variable which is left only, and put that value into the previous one, and then again getting one more variable's value, and so on and so forth. And that's the way we are trying to get the value of other variables. So this is the way that we have solved through the back substitution followed Gauss elimination method with back substitution. Now we want to obviate the need of back substitution, because back substitution seems to be a very different way or very different approach from the Gauss elimination. So if somehow we could get, or we can avoid back substitution, then the process may be easier to solve the system of linear equations. So before trying to understand that, let us look at this form of uh, matrix called reduced row echelon form. So this is a kind of a row echelon matrices. So because you can see here, it already says that the reduced row echelon form matrix should already be in row echelon form. The second requirement says that it has only the pivot values are exactly 1. So the value of the pivot, all the pivots should be 1. Every pivot is 1. So you can see here, every pivot needs to be 1. So every pivot needs to be 1. And then the pivot should be the only non-zero item, non-zero entry in the column. So all other entries in the column should be 0. So how to do that, how we can achieve that? So you can see, like, what we can do, we can in Gauss elimination we are subtracting, or we are adding the suitable scalar multiple of the one equation and add it to another equation. When we say suitable multiple of a particular equation added to another equation, we mean that we want to make certain coefficient, certain variables coefficient is 0. So the suitable multiplier comes from that idea that we want to make something 0. For that, what should be the multiplier? So but we always worked with the previous rows to create a 0 between in the lower equation, or in the equation which is coming later on. Now what we are trying to do now, in this situation, we are trying to create zeros above as well. Because of this pivot, we want to make a 0 in the equations above it. So in the same column, wherever you get the pivot, because of this pivot you want to make the coefficient of the variable for which this pivot is there. You want to make the coefficient of this particular variable from in other equations 0. So that is the idea. By saying that only one non-zero entry in that column, it means that you want to make other equations free from that variable. The coefficient of that particular variable is 0 in all other equations except the equation which contains that pivot value, that 1. So that's what we are trying to do we are taking the suitable multiplier of that equation which contains that row which contains the pivot element, current pivot element, and with this equation, with the help of this equation, we take the suitable multiple of this equation, add it to other equations above it and below it, so as to make the coefficient of that variable 0 in all other equations. So that's what we are trying to do. So let us suppose that we have this system of linear equations. So this is the augmented matrix corresponding to the system of linear equations. This is the augmented matrix. Now, first of all, what we will try to do, we will try to make all the pivots 1. So first pivot, that is this one. This one is the first pivot, which is already 1, and in this particular column, this is the only non-zero entry. So nothing needs to be done for this particular pivot. Now come to the next pivot. This is the another pivot, the minus 10, and we want to make it 1 first. So to make it 1, it is easy that we can replace this particular equation by minus 10 times of this equation. So replacing the row 2 by row 2 divided by minus 10 would do our job. We'll get this particular because of this equation we get this system of linear equations, and it's equivalent, no problem, because you are dividing the whole equation by minus 10. It does not affect the solution set. The number of or the points that are satisfying these two equations is not changed. Now we want to create, instead of in row 1 column 3 there is a element 3, the coefficient value 3, we want to make it 0. So we have to take a suitable multiplier of this equation and add it to the equation number 1, so that this particular place can become 0. So what could be this? This is given by this operation is the possibly correct operation. If we do that, we will get a 0 over here, right? So we can get this 0. So this method is called Gauss Jordan method. Gauss Jordan method is able to create zeros below, in fact creates zeros below as well as above a pivot. In the entire column it creates zeros except that pivot item, pivot entry. So in that particular column, all other values, all other coefficients of that particular variable makes made to be 0. Now let us again see this whole thing with an example. So a fresh look we will see, and we'll try to attempt this particular example with Gauss elimination, with back substitution, as well as with Gauss Jordan method, so that you can see the entire picture of solving the system of linear equations, and you can compare both the systems together. So let us suppose that this is the system of equations that we have. You try to go for the Gauss elimination and you try to make more zeros. So you do all these row operations, and then again all these row operations, and finally you will get this particular augmented matrix. This augmented matrix is actually giving you 2 rows that contain pivot elements. The rest of the 2 rows are entirely 0. The red part is 0, means all the coefficients corresponding to the variables in the last 2 equations are 0. The green zeros are showing that the corresponding constant part is also 0. If it would not have been 0, the constant part would not have been 0, then you are actually saying that 0 times x1 plus 0 times x2 plus 0 times x3 is equals to some constant value which is not 0, which is not possible, which cannot be satisfied by any value of x1, x2, x3, and therefore the system of equation in that case, if instead of these green zeros you have any another constant, the system of equations will not have any solution. But since we are getting zeros on both the sides in the constant part, that is at the green place and as the red place also, both the parts we are getting. So for all the values, all possible values of x1, x2, x3, the variables x1, x2, x3, these two equations will be definitely be satisfied. These two equations will definitely be satisfied for all values of x1, x2, x3. So the compulsion or the restriction is only given by these two equations. So basically these are the two equations that are responsible to identify that set of solutions which is important. Okay, now by the definition of pivot elements, 2 and 7 are the pivot elements because these are the leading elements, leading non-zero elements from the left side um, in that particular row, right? So these are the pivot elements. Now with these pivots, we can go back to the system of linear equations so as to solve it with the back substitution method. Okay, let us just see what has been done. So we find that the first row you have the pivot entries. It is talking about the pivot entries. This is another pivot, this is one pivot entry, another pivot entry, and then we say that x3 is a free variable. Okay, so once you have identified all that, now we want to find out the solution. Now we are actually working with this particular set of equations. So this particular set of equations we are working, so we are actually having this essentially that particular system is equivalent to this system. Now we have two variables, three variables and two equations. Definitely we will have infinite number of solutions because we have one more extra variable. So for any two equations, only two variables are required to solve the system of linear equations, but here you have three variables. So we set the free variable to be 0. Once we set the free variable to be 0, then we have two variables and two equations, and now we can find out the unique solution. So this unique solution is called particular solution. This unique solution is called particular solution, and it can be received as this with the help of back substitution. Once it is done, now you solve the same system of linear equations by making this right hand side part 0. So if we say a coefficient matrix times a variable vector is equals to 0, this matrix equation is corresponding to the system of homogeneous linear equations. Homogeneous means all the terms has same power of variable. So here the power of variable is 1. So x1 to the power 1 or x to the power 1 or x3 to the power 1. So in this particular case where b is non-zero, we have one particular term. This particular term has a non-zero, has this particular term. Okay, let us try to identify this 3, this 3, this 2, both are the coefficient of x1 to the power 0 or x2 to the power 0 or x3 to the x3 to the power 0, while all other coefficients like to this, okay, while all other coefficients like this 2, this 3, this 4, these are the coefficient of x1 to the power 1 or x2 to the power 1 or x3 to the power 1. So these are actually providing the homogeneity in every term. The 3 in on the right hand side of the equality is not having the same power of the variables. So it is not the system of homogeneous linear equations. So we change it to system of homogeneous linear equations by setting these constant parts to 0. Okay, now we are trying to solve it. So we solve it, this particular system of linear equation, for the values that we are getting over here are the values which are able to generate zeros. So what are the values of x1, x2, x3 that generates 0? So the homogeneous system of linear equations are essentially giving us the values of variable vector which are creating zeros, right? So now, since they are creating zeros, so you get xh, all these green means all these things you get. So these are the values of the variable. If you take any value for any k, if you take value of variable vector to be this, then axh will give you definitely equals to 0. Now if you add these two things, the particular solution and the homogeneous solution, and you make it xt, the total solution. Now if you multiply it with the matrix, coefficient matrix A, then what you will get? AXP, A times XP, XH. Now A times XP will always give you the constant B, while AXH will always give you 0. So definitely AXT is equals to B. So that is that will always be satisfied, right? So this is the way we are getting the system of linear equations to be solved for all possible solutions. So you can see the infinite number of solutions are attributed because of this k. This k can take any value in the set of real numbers, right? So this is the crux of getting the solution through Gauss elimination method with the help of followed by back substitution. Now looking at the Gauss Jordan method, we can take the same matrix that we finally got from means after reducing it with the Gauss elimination, we got this matrix, right? We got this matrix, right? So we take this matrix to the again here, and okay, we are back to this matrix, right? So this is the matrix that we are trying. We try to make it in the reduced row echelon form by making the pivots 1 1 and by creating zeros in the entire column except the pivot value. So we get a particular form of matrix. You can notice that okay, you can notice that this cyan colored circle, which is actually giving you an identity matrix. The lower two rows are actually 0 equals to zeros. They are responsible to say like, okay, it is always satisfied. Then this purple circled entries are actually corresponding to the free variables, and the black colored circle, so this thing actually giving you the b dash part. So what is coming out at the constant matrix or the constant value, right? So we can, after doing all these operations with the Gauss elimination, you are actually moving into a form of a matrix which is looking like this. So you have an identity matrix, you have a constant matrix of coefficients corresponding to the free variables, and then you have a b vector, and rest of the things of all the rows are 0 if you have solution, or otherwise you will not have any solution. Okay, once you are getting this thing, you can notice that the variables corresponding to this I2 are basic variables, and the variables corresponding to this free matrix or free coefficient matrix, so this is corresponding to the free variables. So because of these I2, and if you put all the free variables to be 0, then what it becomes? I2 times basic variables or the pivot variables plus f times 0, because you have set all the free variables to be 0, is equals to b21, which means basic variables are equals to b21. It's very straightforward, right? So the particular solution is like this. Very nice. So it is easily visible here, right? Now we want the homogeneous solution. So for the homogeneous solution, we can actually put this constant part entirely 0. So this constant part we can make entirely 0. So once we make it 0, now, and let us divide the variable vector into two parts, the basic variables part and the free variable part. So xb and xf. Once we are able to divide that, we are actually reaching to this situation, right? So you have I, you have f, you have the basic variable part shown or indicated by this purple line, and the green xf is actually showing the free variables, and you want to solve it for 0, 0. Now once you want to solve this, you can see that the solution can be given in this way. So this is the homogeneous system of linear equations, and the solution is given by this thing. So essentially what we are getting, the homogeneous system of equations is having this solution, which is directly visible from this format. From this format, everything is directly visible. So you can see you get the particular solution, that is b210, and when you want to see the homogeneous system of linear equations and homogeneous solution, you are getting minus fi minus f and then I multiplied by xf, the free variables. So because free variables can take any value, you can replace them by any parameter which can take any value, and correspondingly you will get a homogeneous solution. Okay, once you get this homogeneous solution, the total or general solution is given by this red circled value, so which will always give you the all possible solutions of the system of linear equations. And that's how you get your system of linear equation is solved. Okay, so let me take the rest of the part, which is leaving one more creative point in the next video. Thank you.